The 2026 Tesla Model 2 is turning heads before it even hits the road. What new surprises does Tesla hide under its sleek exterior? And how does the interior really stack up for everyday drivers like you? In this video, we're compiling the latest reports and leaks. So while some details might look familiar, you can bet there are plenty of new insights waiting for you. If you don't want to miss a single Tesla update, smash that subscribe button, hit the bell, and be among the first to unlock every secret Tesla hides. Let's get Autogearshift to 15,555 subscribers. Come on, be part of the first crew. Now, it's time to begin. Earlier, a few new images surfaced from Tesla's crash test and recycling facility at Giga, Texas, showing a disassembled Cybercab prototype. We can clearly see its hood, seats, and several trim pieces stacked in collection bins, along with nearly 10 Cybercabs covered in white wraps. What's interesting is that most of them, even the wrapped ones, appear to have side mirrors, something Tesla once said it would eliminate. And that small detail connects directly to the upcoming Model 2, the company's most anticipated $13,579 EV. Before we dive in, what if I told you Tesla's cheapest car might have the smartest interior ever built? And Elon Musk himself called this design a game changer for the next decade. Means in a mass-market EV. The entire cabin is built using a new biocomposite material blend that's 30% lighter than traditional synthetic leather, yet just as durable and resistant to daily wear. Every surface you touch, from the dashboard to the door panels, is formed from a single recyclable matrix that cuts manufacturing complexity and total vehicle weight. According to Tesla, each Model 2 interior reduces the use of raw materials by 22 kilograms compared to a standard Model 3, a small number that translates to thousands of tons saved annually once full-scale production begins. But sustainability here isn't just about what's removed, it's about what's improved. Traditional interiors require multiple paint and coating layers to achieve their final color. The Model 2's panels skip that process entirely. The pigments are baked directly into the biocomposite itself, eliminating the need for any volatile organic compounds (VOCs) during manufacturing. That means zero toxic paint emissions from Tesla's interior line. A key step toward the company's build once, recycle forever philosophy. The payoff goes beyond environmental points. Removing paint layers and adhesives makes the surfaces easier to refurbish and recycle at end of life, reducing material recovery costs by nearly 40%. It also allows Tesla to standardize interior parts globally without adjusting for regional chemical regulations, cutting production time by several hours per vehicle. How is Tesla's new one-screen dashboard the smartest and most efficient ever built? Inside the 2026 Tesla Model 2, the traditional cockpit layout is gone. Tesla has rebuilt the dashboard from the ground up around a single 10.5-inch center display, smaller than the 15-inch screen found in the Model 3 and Y, but engineered for maximum clarity and efficiency. The new OLED panel, co-developed with LG Display, delivers up to 2,000 nits of brightness, nearly double the Model 3's 1,100 nit LCD. That means no more glare issues even under direct sunlight, while power consumption drops by about 18%, extending range by an estimated 6 miles on longer drives. The driver's view is stripped back. No digital cluster behind the steering wheel, no physical buttons, no stalks. Instead, Tesla uses a head-up projection system that projects essential speed, navigation, and autopilot data onto the lower windshield. The system runs on the same compute platform as FSD version 12, pulling live data from the car's perception stack to adjust brightness and layout dynamically based on lighting conditions and driving speed. But where the Model 2 truly stands out is its voice-driven AI interface, which replaces almost every manual input. It's trained on billions of voice samples collected from Tesla's global fleet, allowing it to recognize not just words, but intent. For instance, when you say, "Set cabin to road trip mode," the car executes a multi-layer routine, softening seat firmness by 10%, lowering cabin temperature by 2 degrees Fahrenheit, and switching the sound system from directional to spatial mode for reduced fatigue over long distances. This is what Elon Musk meant when he called the Model 2's interior a thinking cabin. It's not about adding more screens or controls. It's about removing everything that slows down the connection between driver and machine. One screen, zero waste, and a system that quietly gets smarter every time you drive. So tell me, would you trade traditional buttons for a car that actually thinks with you? Comment 1 if you're ready for this AI-driven future, or 2 if you still want full manual control. How is Tesla's learning wheel the future of driver interaction? Internally referred to as the learning wheel, this redesigned unit combines physical precision with adaptive intelligence. The most striking change: there are no stalks and no gear selector. Everything, from drive modes to turn signals, is controlled through touch-sensitive zones integrated into the steering surface and linked directly to the car's AI input system. Beneath the minimalist design lies a dense array of pressure and motion sensors embedded under the rim. These sensors continuously track the driver's grip and torque input, adjusting steering resistance in real time. In city mode, the wheel feels light and highly responsive, ideal for tight maneuvers and frequent stops. Once on the highway, the same wheel automatically stiffens, adding stability and weight to prevent overcorrection at higher speeds. According to Tesla's internal data, this adaptive mechanism reduces driver reaction time by roughly 80 milliseconds compared to conventional mechanical steering columns. That might sound small, but at 60 miles per hour, it translates to over 7 feet of stopping distance, enough to make a measurable difference in emergency scenarios. From a manufacturing standpoint, the learning wheel is also designed for scalability. One standardized unit can be installed across all global variants, whether left or right-hand drive, cutting costs by up to 15% per vehicle and simplifying logistics across gigafactories. How are Tesla's new seats proof that comfort can be engineered? Smarter, not softer? In the 2026 Tesla Model 2, the seats aren't just redesigned. They're re-engineered from the molecular level up. Tesla calls this new approach the foam shell architecture, which integrates the seat's frame and padding into one continuous molded structure. This shift eliminates nearly 37 individual components found in the Model 3 seat assembly, cutting total seat weight by 15% and lowering production costs by roughly 12% per unit. The design also reduces cabin mass by about 9 kilograms, translating to a small but measurable 0.4% improvement in driving range. Each seat is formed from recycled polymer foam, derived directly from Model Y factory offcuts that would otherwise be scrapped. Tesla claims this reuse strategy diverts nearly 120 tons of waste material per year from landfills across its Fremont and Shanghai gigafactories. Despite being lighter, the seats still pass all FMVSS 207 and ECER 17 crash and load tests, maintaining over 98% structural retention after repeated stress simulations equivalent to 10 years of daily use. Inside the surface, Tesla embeds a micro-pressure sensor grid, roughly 120 sensors across the backrest and cushion, capable of sampling posture and pressure distribution up to 200 times per second. This data allows the system to dynamically adjust lumbar support and heating zones in real time. The AI model behind it, trained on aggregated biometric feedback from over 1.5 million Tesla vehicles, detects subtle shifts in body weight and predicts when a driver may be fatigued or uncomfortable. When you enter the car, the seat automatically recalls your saved driver profile, then spends the first 10 minutes of driving subtly rebalancing pressure points to match your most recent posture data. Tesla's internal studies show this reduces lower back strain by 23% and improves blood circulation metrics by 17% on drives longer than an hour. How Tesla's hidden HVAC system in the 2026 Model 2. quietly changes everything. Tesla is taking another big step in cabin comfort with the 2026 Model 2, and this time, it's all about what you can't see. The company continues the invisible air vent design first seen on the Model 3 Highland, but the new Model 2 goes far deeper in engineering. Instead of using around 40 traditional flaps and louvers like most compact EVs, the Model 2 relies on just 16 digitally controlled microvalves. That's a 60% cut in mechanical parts, which means fewer rattles, less dust buildup, and fewer maintenance issues over time. Noise tests from Fremont's prototype line show cabin sound levels dropping by about 4 decibels compared to the Highland, roughly the difference between a quiet library and a normal office. The airflow is smoother too. Sensors monitor cabin temperature at over 20 points per second, balancing the stream automatically to keep hot and cold zones within just 1 degree Celsius of each other. In other words, no more freezing hands and warm feet during long drives. The system's precision also brings measurable efficiency gains. Tesla engineers report that the new HVAC uses about 15% less power than the one in the Model 3 Highland. For the Model 2's expected 50 kilowatt-hour battery pack, that translates to around 0.8 kilowatt-hours saved every 100 kilometers, or about 12 to 15 miles of extra range per full charge, depending on conditions. In a vehicle expected to cost under $30,000, that's real value most drivers can feel. And then comes the part that sounds almost sci-fi: the new voice AI. Drivers can say things like, "Send cool air to my left hand," or "Warm up my feet," and the system reacts instantly. Cabin cameras and infrared sensors detect where you're sitting and redirect airflow with centimeter-level accuracy. It's no longer just about setting a temperature. It's about directing comfort exactly where you want it. That's the inside. How about the outside? According to fresh leaks out of Gigafactory Shanghai and early design blueprints believed to be from Tesla, the Model 2 won't just be a smaller Model 3. Tesla change. Why are some early testers calling it the best-looking budget EV ever? And could this new body design make Tesla's cheapest car feel like a premium model? How can a two-door Tesla really be roomier? Tesla's 2026 Model 2 breaks tradition in more ways than one. For the first time in the company's history, a two-door hatchback joins its lineup. Compact on the outside, yet cleverly engineered to outperform expectations on space, structure, and manufacturing speed. While most Tesla vehicles stretch past the 4.6-meter mark, the Model 2 comes in at roughly 4,050 millimeters long, 1,790 millimeters wide, and 1,440 millimeters tall, making it about 230 millimeters shorter and 80 millimeters lower than the Model 3. Despite that smaller footprint, Tesla has squeezed out up to 20% more usable interior volume, bringing total cargo and cabin space to around 2,450 liters combined. A feat achieved through precision packaging and a reimagined roofline. The secret lies in the new hatchback rear architecture. A steeply sloped C-pillar and elevated tailgate allow for a 480-liter cargo bay with the rear seats folded, roughly 75 liters more than the Model 3 offers. The flat-load floor is made possible by relocating the rear motor slightly forward and integrating the cooling modules beneath the subframe. This not only creates a deeper trunk floor, but also improves aerodynamics by streamlining the rear underbody airflow. Even with only 2 doors, Tesla has optimized ingress and egress using 1.15-meter wide front openings and longer door hinges that extend up to 37 degrees, comparable to what's found on compact coupes like the BMW 2 Series. Inside, the slimmer seats and reduced dashboard depth have freed up 42 millimeters of extra knee room for rear passengers, a subtle but crucial improvement for short-distance urban rides. In tight city spaces, the car's agility stands out. The new steering geometry gives the Model 2 a turning circle of just 5.15 meters, tighter than a Mazda MX-5 Miata's 5.3 meters, allowing it to U-turn on streets where most EVs would struggle. Combined with a curb weight expected to be under 1,450 kilograms, thanks to the 9,000-ton Gigapress single-piece rear casting, the Model 2 becomes not only nimble but also structurally superior. Tesla's engineers report a 40% reduction in welding points and a 67% cut in assembly time, with manufacturing energy consumption down by 30% compared to the Model 3's steel body. How can one LED strip save 25% more energy? Tesla's decision to ditch traditional dual headlights for a single full-width LED light bar on the 2026 Model 2 marks one of its boldest exterior redesigns yet. Spanning 1,370 millimeters across the front fascia, this unified lighting system mirrors the Cybertruck's minimalist DNA. But beneath that sleek surface lies a deep engineering overhaul. According to early technical data shared by suppliers in Shanghai, the new monoline LED array operates at 9.8 volts instead of the typical 12 volts, powered by next-gen Osram Aslan black flat chips. Each module outputs roughly 1,800 lumens per watt, allowing the entire lighting system to consume just 92 watts under full beam operation, a 25% reduction compared to the 122 watts drawn by the Model 3 Highland's dual-beam setup. In night driving tests, this translates to an additional 4 to 5 miles of real-world range over a 300-mile charge cycle. Durability is another key advantage. Traditional headlamp assemblies rely on two separate housings, each containing multiple boards, connectors, and cooling elements. Tesla's new design merges everything into one sealed aluminum housing, with a single printed circuit board PCB and one high-voltage connector, cutting the number of electrical joints from 46 down to just 18. That simplification reduces potential electrical failure points, lowers part costs by roughly $85 per vehicle, and trims 1.6 kilograms off the car's nose. Tesla's testing data shows a 12% increase in beam distance, now reaching nearly 155 meters on high beam, thanks to a new vacuum-sputtered reflective coating applied to the inner housing. This coating improves directional focus without adding extra LEDs, giving the Model 2 better road illumination than the Model 3 Highland, while maintaining a tighter beam spread to reduce glare. How can Tesla really ditch paint? One of the most surprising changes to the 2026 Tesla Model 2 isn't something you'll see. It's what the car is made of. Tesla has developed a new steel aluminum manganese alloy for the Model 2's body structure, designed to strike the perfect balance between strength, weight, and cost. This new alloy makes the Model 2's body about 8% lighter than the Model 3, roughly 45 kilograms less overall, yet it's also 15% stiffer, meaning the frame resists bending or twisting more effectively. In testing, that extra stiffness cuts structural flex by about 20 Newton-meters per degree, so the car feels tighter in corners and more stable during impacts. But the most radical development is in how Tesla plans to finish the body, or rather, not finish it at all. Engineers are testing a new dry coat finish process, which eliminates traditional wet painting altogether. Instead of multiple primer, base, and clear coat layers that can cost up to $3,000 per vehicle, the dry coat method uses a vapor-deposited protective film that bonds directly to the alloy surface. This treatment gives the metal a natural satin texture resistant to scratches, oxidation, and UV fading. And because the color is inherent to the alloy itself, there's no paint to chip, fade, or peel over time. If the trials at Gigafactory Shanghai succeed, the Model 2 could become Tesla's first unpainted production vehicle, a move that would not only reduce factory emissions by roughly 40 kilograms of CO2 per car, but also simplify recycling at the end of the vehicle's life cycle. For buyers, it means less maintenance, less worry about paint damage, and a car that keeps its futuristic look for decades, all while being stronger, lighter, and cleaner to build. How are new door handles and mirrors the most practical change Tesla has ever made? Tesla's 2026 Model 2 might look minimal at first glance, but two of its smallest exterior parts, the door handles and mirrors, have received engineering-level attention that's anything but minor. The new horizontal pull-style handle replaces the older flush-mounted design, cutting the opening force down from around 30 newtons to just 18 newtons. In cold climate testing at -5 degrees Celsius, this new handle mechanism maintained full operation through 980 of 1,000 test cycles, while the old Model 3 handle failed intermittently after about 170 cycles due to frost buildup. Tesla also simplified the internal linkage, reducing the moving parts from 9 to 5, which lowers long-term mechanical wear and speeds up service replacements by nearly a minute per door. The side mirrors tell a similar story of refinement through numbers. Their reflective surface area has been expanded from 35 to 39 square inches, giving the driver an extra 4 inches of visibility width on each side. That seemingly small increase reduces the side blind zone to less than 1.9 degrees, tighter than any compact EV currently sold in North America. The new mirror housing is sculpted to cut aerodynamic drag by 0.003 in drag coefficient. That's equivalent to roughly 5 extra miles of real-world driving range on a full charge. Each mirror also uses a dual-motor folding system tied to the car's rear radar, automatically retracting when it senses an obstacle closer than 30 centimeters. How can a $15,000 hatchback really match Porsche-level aerodynamics? 2026. Model 2's integrated rear body design now achieves a drag coefficient of just 0.22 CD, the same figure claimed by the Porsche Taycan, a car that costs nearly 3 times as much to build. Every 0.01 reduction in CD typically adds about 8 to 10 kilometers of range at highway speeds, and the Model 2's streamlined tail contributes a significant share of that efficiency gain. A hidden rear spoiler, molded directly into the tail structure, generates roughly 18 kilograms of downforce at 110 kilometers per hour, giving the lightweight hatchback noticeably better stability in crosswinds and high-speed lane changes. In Tesla's internal track data, lateral body sway dropped by nearly 7% compared to early prototypes without the spoiler, translating to tighter cornering and smoother steering feedback above 100 kilometers per hour. Completing the package are Tesla's new 17-inch Aeroflow wheels, which feature closed face inserts and a redesigned airflow pattern around the brake housing. Each wheel cuts rotational drag by about 6 Newton-meters compared to the Model 3's base rims, improving the car's total energy efficiency by around 5.4%. In real-world driving, that means an extra 22 to 25 kilometers of range per full charge, without touching the battery pack. So, if you could pick just one feature to see on your next Tesla, which would it be? Comment 1 for the new hatchback body, 2 for the LED light bar, 3 for the unpainted alloy shell, 4 for the smarter handles and mirrors, or 5 for the aero tail and wheels. And tell us why in the comments below. Breaking news. Tesla chairwoman Robin Denholm just made it official.
We do have a few other vehicles coming out, so he spends time on that. He's spending time on everything across the board.
It's the first confirmed statement from Tesla's top leadership after months of silence about the long-awaited Model 2. So, how close are we to finally seeing the under $15,789 Tesla Model 2? Where will it be built? Mexico, Berlin, or Shanghai? How is Tesla finally getting ready for Model 2? When Tesla chairwoman Robin Denholm recently said, "We have new vehicles coming out," she didn't use the word vehicle. She said vehicles in plural. That subtle difference matters. It means Tesla isn't just working on one model, but at least 2 new cars. Industry watchers believe one is the long-awaited Tesla Model 2, and the other could be a smaller compact crossover using the same new platform. For months, Tesla fans and investors have been waiting for official confirmation that the Model 2 project is still alive. Now, with Robin's statement, that signal finally arrived. And it's coming at a critical time for Tesla. After recording its slowest quarter of 2024, with global deliveries falling to around 386,000 vehicles, down 8% year-over-year. Tesla needs a new mass-market product to restore growth momentum. Elon Musk has already shared key details about the Model 2. It will be built on Tesla's Gen 3 platform, a completely new manufacturing system designed to cut production costs by up to 50% compared to the Model 3. To put that in perspective, the current Model 3 costs roughly $26,000 to produce, so the Model 2 could be built for around $15,000 or even less. That price range would finally let Tesla compete head-to-head with Chinese EV giants like BYD and Xiaomi, whose small electric cars currently sell between $10,000 and $15,000. Experts say Tesla needs to act soon. BYD sold over 3 million EVs in 2024, while Tesla delivered just under 1.8 million. The market is shifting toward affordable electric cars, and Tesla can't rely only on premium models anymore. After all these hints from Elon and Robin, do you believe production is really about to begin? If you think the Model 2 is ready, drop a Model 2 yes in the comments. Where will Model 2 be built? Right now, Tesla's biggest mystery isn't the design of the Model 2. It's where Elon Musk plans to build it. Robin Denholm's comment about new vehicles made one thing clear. Tesla is preparing for mass production on a new scale. But that raises a crucial question. Which factory will take the lead? Let's start with Giga Mexico, announced back in March 2023. At the time, Musk called it the next major step for the company and confirmed it would produce cars based on the Gen 3 platform, designed to cut manufacturing costs by 50% compared to the Model 3 and Y. The new site, located in Nuevo León, covers over 4,000 acres, nearly double the size of Giga Texas, giving Tesla plenty of room for future expansion. But nearly 2 years later, the site is still not operational. Local reports show only early groundwork is complete, as infrastructure, water, and energy access remain limited. Sources from the Mexican government suggest full construction might not begin until late 2025. That delay matters. If Mexico isn't ready, Tesla can't afford to wait, especially when its global sales growth has slowed sharply since mid-2024. On the bright side, labor costs in Mexico are 30 to 40% lower than in the U.S., and average auto wages are around $3 to $4 per hour, compared to $9 to $10 per hour in Texas. This makes Giga Mexico the cheapest production option long-term. However, the country also brings logistics challenges and border bureaucracy, which could delay shipping parts or vehicles to the U.S. and Canada. Political shifts after the next Mexican election may also affect Tesla's incentives or tax policies. Meanwhile, Giga Berlin in Germany has quietly become one of Tesla's most flexible plants. It's currently producing over 6,000 Model Ys per week, and its advanced automation lines can be retooled in under 90 days to build a new vehicle type. This flexibility makes Berlin a perfect candidate for the first wave of Model 2 production, especially since demand for small, affordable EVs in Europe is booming. Industry data shows sales of sub-$25,000 EVs in Europe jumped 45% year-over-year in 2024, while Tesla's Model 3 sales declined in the same period. Elon Musk himself hinted that Berlin might surprise people next year, a remark many analysts now see as a signal that Model 2 pilot runs could start there as early as the fourth quarter of 2025. Then there's Giga Shanghai, Tesla's most efficient and profitable factory to date. The plant currently accounts for more than 50% of Tesla's global deliveries, and its production cost per vehicle is about 25% lower than in the US. Shanghai's major advantage is its supply chain. It already works with CATL and BYD for sodium-ion batteries and other low-cost materials, making it the ideal testing ground for Tesla's budget EV line. Analysts from TrendForce believe Shanghai could launch pilot production of the Model 2 by mid-2025, ahead of full-scale rollout in 2026. If Tesla truly plans to launch the Model 2 globally in 2026, production must begin by late 2025 at the latest. Most experts predict Shanghai or Berlin will take the lead due to their readiness and established supply chains, while Mexico will follow once construction catches up. The exact order could define everything, from how affordable the Model 2 becomes, to how fast Tesla can compete against BYD's Seagull $10,000 and Xiaomi's SU7 Lite $14,000 in the global EV price war. How can Tesla hit $15,000? When Elon Musk first teased the Model 2, he made a bold promise. It'll cost half of a Model 3. For a brand that once defined the premium EV segment, cutting costs by nearly 50% sounds extreme. But Tesla has a clear plan built around three pillars: manufacturing innovation, new battery chemistry, and smart localization. The first and biggest piece of the puzzle is the Gen 3 platform, combined with Tesla's unboxed manufacturing process. Unlike traditional production lines where cars move step by step along a conveyor, Tesla's new system builds front, rear, and battery modules separately and assembles them at the end, similar to how airplanes are built. Musk said this could cut factory space requirements by 40% and reduce assembly costs by 30 to 50%. On top of that, Tesla's giga-casting technology replaces dozens of smaller metal parts with single-piece aluminum castings, further simplifying production. The second cost-saving breakthrough comes from battery technology. Instead of relying on expensive lithium-ion cells that use cobalt and nickel, Tesla is preparing to switch to sodium-ion or aluminum-ion chemistry for the Model 2. Sodium and aluminum are far more abundant and cheaper. Industry estimates show sodium-ion packs could cost around $55 per kilowatt-hour, compared to $90 to $100 for lithium-ion, a 20 to 30% reduction in raw material cost. They're also safer under high heat and more sustainable, a big plus for large-scale production. Combined with the structural battery design Tesla already uses, this move could make the Model 2 the most cost-efficient EV Tesla has ever built. The third factor is location and labor. By manufacturing in Mexico or China, Tesla can leverage lower production costs across the board. Labor alone in those markets runs 25 to 35% cheaper than in the US or Germany, while local supply chains for materials and batteries are already in place. Building in Shanghai or Nuevo Leon also means shorter logistics routes to key suppliers, helping Tesla save millions in shipping and tariffs. Of course, Tesla's $15,000 target isn't just about beating its own cost curve. It's about outpacing China's budget EV giants. The BYD Seagull sells for around $9,000, and the Wuling Bingo starts near $8,700, but both have shorter range and lower performance. If Tesla can deliver a Model 2 with 250 miles of range, full OTA updates, and FSD-ready hardware, all at around $15,000, it would be the most affordable long-range EV ever built by a Western automaker. How can Tesla really deliver by 2026? After months of silence, Tesla finally seems to be positioning the Model 2 for a real debut window. Based on internal leaks, supplier reports, and recent board statements, the company's roadmap now looks more defined than ever, but also tighter than most analysts expected. If everything stays on track, Tesla's timeline for the $15,000 compact EV could unfold as follows. Finalize the main production site by the first quarter of 2025, begin pilot manufacturing by Q4 2025, and start mass production between Q1 and Q2 of 2026, with a public launch event by mid-2026. That's an ambitious schedule, especially for a car expected to redefine Tesla's business model. Historically, even Tesla's most successful models have faced delays. The Model 3, announced in 2016, reached volume production more than a year late, and the Cybertruck took nearly 4 years to move from prototype to customer delivery. Unlike those vehicles, however, the Model 2 is meant to rely on Tesla's existing manufacturing backbone rather than brand new hardware or materials. That could help speed up execution, but only if the Gen 3 production lines and new battery technologies scale as planned. Which factory do you think will roll out the first Model 2? Shanghai, Berlin, or Mexico? In the latest flyover footage from Joe Tegmeyer at Tesla's Gigafactory Texas in Austin, hundreds of compact vehicle bodies are being assembled simultaneously. Based on their smaller size and production layout, analysts believe these could be Tesla's long-rumored Model 2 prototypes. Meanwhile, over at Fremont Factory, similar test units have been spotted moving through evaluation zones, while the Cybercab continues internal crash testing. All signs suggest Tesla has entered the pre-production phase for its next-gen Platform 1, NGP1, the same architecture that may also underpin the company's next surprise, the Tesla Model 2. Feature number 1. Next-gen platform. How can Tesla build a car 40% cheaper and 50% faster than the Model 3? During Tesla's 2025 Q2 earnings call, we got some leaks about what insiders had been whispering for months. The Model 2 will ride on the company's brand new next-gen Platform 1. But this isn't just another platform update. According to leaked internal documents, NGP1 is designed to cut total production cost per unit by about 40%, compared with the Model 3, while slashing assembly time by roughly half. The key lies in a full redesign of how a Tesla is built, not just what it's built from. Instead of a linear production line that moves a half-finished car through dozens of stations, the new unboxed process splits the Model 2 into 5 large modules, each built separately by dedicated robot clusters. These modules, the front and rear castings, the battery floor structure, the cabin interior, and the upper shell, are then brought together for final assembly that takes less than 5 minutes, compared with nearly 20 on a Model 3 line. This parallel workflow allows one NGP1 line to push out a finished car roughly every 37 seconds, almost twice as fast as Tesla's current factories. That efficiency is amplified by Tesla's third-generation gigacasting system. The Model 3's body is made from 171 individual metal pieces welded together. The Model 2 will use just 2 massive aluminum castings, one for the front, one for the rear, each weighing around 110 kilograms. Formed under up to 9,500 tons of pressure, these castings reduce total body weight by about 15% and boost structural rigidity by roughly 20%. The streamlined design cuts labor time in the body shop by nearly a third and trims the number of welding robots per line from 300 to about 120. The supply chain gets the same treatment. By reducing total component varieties by almost half and simplifying logistics routes, Tesla expects inbound shipping and handling costs to fall by about 30%. Each gigafactory using the next-gen setup can now produce close to 2 million vehicles a year, roughly double the output of a Model 3 plant of similar size. Financially, the math is just as aggressive. The capital cost per annual vehicle output drops from roughly $3.5 billion for a Model 3 line to about $2 billion under NGP1. Operating cost per unit falls from $31,000 to $18,200, cutting the payback time for new factories from 3.5 years to under 2. Those numbers make it possible for Tesla to price the Model 2 around $17,800 to $19,000, a figure once thought impossible outside China. For comparison, the BYD Seagull sells at $10,500 and the Wuling Mini EV at $5,000, but both rely on much cheaper labor and smaller form factors. The difference is, Tesla can now compete head-on with them from North America or Mexico, not just from China. Feature number 2. Aluminum-ion battery. Can Tesla's 2026 breakthrough end China's grip on EV batteries? According to internal documents and early lab data, the upcoming aluminum-ion Al-ion cells are targeting an energy density of around 300 watt-hours per kilogram, up from 180 to 200 watt-hours per kilogram on Tesla's current LFP cells used in Model 3 and Model Y standard range vehicles. That's roughly a 60% increase in energy density, meaning Tesla can achieve the same 300-mile range using a 30 to 35% smaller and lighter battery pack. In practice, that could shave up to 180 kilograms from the Model 2's curb weight, improving both acceleration and efficiency. Charging speed is where the chemistry really shines. Thanks to the extremely high mobility of trivalent aluminum ions, Al3+, and the use of graphene composite anodes with conductivity exceeding 1 million square meters per meter, Tesla's latest prototypes have achieved 0 to 80% charge in under 8 minutes, using a 350 kilowatt DC charger. For comparison, the Model 3 LFP pack needs around 25 minutes for the same charge. Thermal tests show negligible degradation even under 10C charge rates, suggesting the Model 2 could reclaim 150 miles of range in about 5 minutes, faster than most refueling stops. Durability is equally impressive. Laboratory cycle testing performed with Rocket Lab's equipment indicates 12,000 full charge-discharge cycles, equivalent to more than 1.8 million kilometers of real-world driving. That's 2.5 times the cycle life of current LFP chemistry, and about 5 times longer than high-nickel NCA packs used in the Model S and Model X. Even after 10,000 cycles, cell capacity retention remains at 91%, while internal resistance growth stays under 2 milliohms, a record low figure in EV battery testing. Perhaps the most underrated advantage lies in the chemistry's thermal stability. The aluminum ion cell operates safely from -30 degrees Celsius up to +90 degrees Celsius, far wider than the -10 degrees Celsius to +55 degrees Celsius envelope of most lithium cells. This wide thermal margin means Tesla can eliminate heavy liquid cooling loops and complex heat pumps entirely, saving $400 to $600 per car in hardware and improving reliability in extreme climates, from Canadian winters to Texan summers. From a cost perspective, the numbers are game-changing. With aluminum and graphene being far more abundant than lithium or nickel, raw material cost per kilowatt-hour could drop by 28 to 30%, putting pack-level costs close to $58 per kilowatt-hour, down from roughly $80 per kilowatt-hour for current LFP packs. If achieved at scale, this would push the total battery cost for the Model 2 below $5,000, an unprecedented milestone in modern EV manufacturing. Production is already being mapped out. Gigafactory Texas is slated to host the first pilot aluminum-ion cell line by Q3 2026, with an estimated initial capacity of 15 gigawatt-hours per year, enough for about 400,000 Model 2 units annually. Tesla insiders suggest the line could ramp to 75 gigawatt-hours by 2028, rivaling BYD's Blade battery output. But beyond all these specs lies a deeper motive: independence from China's supply chain. At present, China refines nearly 70% of the world's lithium, 63% of nickel sulfate, and over 80% of graphite anode materials. By transitioning to aluminum-ion chemistry, Tesla effectively bypasses those choke points. Aluminum is the most abundant metal in the Earth's crust, and North America already refines over 4.5 million metric tons annually, providing a fully domestic pathway for EV battery production. Feature number 3, AI-driven cabin and HW5 autonomy. Can Tesla's next brain outthink China's smart EVs? The third pillar of the 2026 Model 2 isn't about what's under the hood, it's about what's behind the wheel. For the first time, Tesla is equipping a mass-market car with its HW5 autopilot computer, a custom silicon platform fully designed in-house by the Dojo AI team. With 500 trillion operations per second, TOPS of processing power, HW5 doubles the performance of HW4 while consuming just 60% of its energy, placing it within reach of NVIDIA's Thor chip, which many Chinese automakers plan to use in 2025. In other words, Tesla's smallest car will run on one of the most efficient AI brains ever put in a vehicle. But hardware alone doesn't define the upgrade. The Model 2's interior is built around a voice-first and vision-aware environment, moving away from Tesla's signature large touchscreen and toward a cabin that reacts to the driver rather than being controlled by them. Using an integrated eye tracking and facial recognition system, the car identifies who's sitting inside, automatically adjusts seat position, climate settings, and even the heads-up display layout to match the driver's preferred style. It's the first Tesla designed to feel personal from the moment you step in. The system's onboard AI doesn't just respond, it learns. After roughly 2 weeks of driving data, it begins predicting user routines, suggesting optimal charging times based on local energy prices and recommending routes that balance speed, weather, and traffic conditions. Tesla engineers describe it as a proactive co-pilot, powered by a lightweight neural model trained directly on Dojo supercomputers. On the autonomy front, the HW5 platform is built to run Tesla's Level 4 full self-driving software, which is now in internal testing at the Fremont track. Early data from those tests show 99.2% accuracy in complex urban scenarios such as multi-lane merges, unprotected left turns, and dynamic pedestrian crossings, performance metrics no Chinese EV maker has yet matched. BYD, NIO, and XPENG still rely on third-party stacks from NVIDIA or Mobileye, giving Tesla a critical edge by owning its full AI pipeline, from silicon to software. The result is a cabin that not only recognizes its driver, but also thinks ahead of them, merging Tesla's FSD intelligence with the personal adaptability of next-gen consumer tech. For buyers used to static infotainment systems, the Model 2 could feel more like interacting with a digital assistant than a car interface. Feature number 4. Butterfly door. Why would Musk choose such an exotic design for Tesla's cheapest model? On October 10th, Tesla was spotted for the first time testing the Cybercab prototype at its Fremont factory in California, signaling that Elon Musk's long-awaited robo-taxi project is finally taking shape. But eagle-eyed fans noticed something unusual. The door design looked nothing like any current Tesla. Wide hinges, high arc movement, a possible hint of butterfly doors. That detail quickly reignited speculation that the upcoming 2026 Tesla Model 2 and Cybercab might share the same compact platform, and maybe the same dramatic door mechanism. How does Tesla's butterfly door actually work? At first glance, the 2026 Tesla Model 2's butterfly door may look like a stylistic flourish, a design play to attract attention. But a deeper look at its structure shows it's an engineering-driven innovation built for efficiency, safety, and practicality. The door opens at a 65 to 70-degree vertical arc, enabled by an off-centered dual-pivot hinge system that lifts the panel both upward and outward in a smooth compound motion. The geometry provides a clearance radius of about 780 millimeters, compared to nearly 1,100 millimeters on a conventional side-hinged sedan door, cutting required lateral space by over 30%, a crucial improvement for urban environments where parking widths average just 2.4 meters in U.S. cities. Mechanically, Tesla's system combines one precision electric actuator rated for up to 18,000 open-close cycles with a miniature hydraulic piston, delivering a lift force of 1.9 to 2.1 kilonewtons. Together, they create a balanced opening motion without the need for complex load distribution sensors or multi-link hinges like the Model X's Falcon Wing, which required 7 individual sensors per door. This simplification cuts total parts count by 62%, reduces maintenance points, and slashes the production cost to about $1,200 to $1,500 per door, roughly 70% cheaper than the Model X system that cost nearly $5,000 per side to build and service. Each butterfly door weighs between 24 and 27 kilograms, a full 30% lighter than the Model 3's 36 to 38 kilogram steel panel doors. This weight reduction was achieved through the use of 7075 T6 aluminum alloy in both the hinge and frame sections. This aerospace-grade alloy boasts a tensile strength of 570 megapascals and a yield strength near 500 megapascals, yet remains 40% lighter than high-carbon automotive steel. The result is not only faster actuation, but also lower inertial load on the hinge assembly, extending its operational lifespan to an estimated 10 years or 150,000 cycles under normal use. The lighter mechanism also yields measurable energy savings. Each full open-close operation consumes approximately 0.15 kilowatt-hours, equivalent to 0.02% of the Model 2's estimated 40 kilowatt-hour battery pack, or about the energy needed to drive 120 meters. Over 10 years of typical use, around 6 openings per day, the cumulative energy draw would total only 330 kilowatt-hours, a negligible amount compared to total lifetime energy throughput. Moreover, by reducing door weight and frictional drag, Tesla's simulations suggest a 0.005 drop in drag coefficient, CD, improving aerodynamic efficiency enough to extend driving range by roughly 2 to 3 kilometers per full charge. Structurally, the butterfly door exceeds standard safety benchmarks. In compression tests, the assembly withstands 6.8 kilonewtons of lateral force, about 15% higher than standard side doors, ensuring crash resistance during side impacts. The reinforced hinge mounts distribute load across 3 anchor points tied into the Model 2's front A-pillar and roof rail, maintaining cabin integrity during a collision. So, is this the kind of innovation you've been waiting for in the Model 2? Comment yes if the butterfly door's design impresses you, or drop the feature name, in 2 to 3 words, you're most excited to see Tesla add next. Why Tesla's butterfly door could be a lifesaver for aging drivers. For many American drivers, the daily act of getting in and out of a car isn't just inconvenient, it's physically demanding. According to data from the National Institute on Aging, 2023, nearly 47% of U.S. adults aged 60 and above experience some degree of lower back discomfort linked to repetitive bending, while 1 in 3 report knee or hip stiffness that makes conventional sedan access difficult. Tesla's new butterfly door on the 2026 Model 2 appears to directly address that growing demographic challenge with a design that quietly merges style with biomechanical relief. The door's 1.45 to 1.6 meter vertical clearance allows older drivers to exit the car while maintaining an upright spine angle, cutting lumbar compression by roughly 38%, according to internal ergonomic modeling. In traditional sedans, the required 40 to 50 degree forward lean multiplies spinal pressure 1.6 to 2.1 times compared to standing, which can trigger pain flare-ups or disc inflammation over years of use. By reducing the bend angle to around 20 degrees, Tesla effectively shifts this daily movement from a strain-heavy action into a natural stepping motion, something that's especially valuable for seniors with reduced core stability or hip mobility. The gains don't stop there. The door's wide arc and dual pivot design also decrease knee torque by 35%, helping older adults who struggle with arthritis or meniscus degeneration. For context, that reduction in torque equals about 40 to 45 Newton-meters less force on the joint per movement, a meaningful margin when repeated hundreds of times per month. In a 2024 Biomechanics Institute of Berlin test participants aged 55 to 70 cut their average entry-exit time from 4.2 seconds to 2.8 seconds, while their range of motion improved by 18%, suggesting smoother, more confident mobility. Tesla's engineers further leveraged the butterfly layout to raise the seat base from 460 to 490 millimeters, bringing it close to crossover height. That allows a 100 to 105 degree hip-to-torso angle, the sweet spot recommended by the American Society of Biomechanics for minimizing lower back tension. For older drivers, this means less falling into a low seat and easier balance recovery when standing up. a key safety factor that often goes unnoticed in vehicle design. How could the butterfly door redefine what affordable Tesla really means? Tesla's next major experiment in cost engineering and perception design is already in motion. According to early production schedules leaked from Giga Berlin, the first functional prototype of the 2026 Tesla Model 2 equipped with butterfly doors is slated for reveal in Q2 2026, followed by homologation testing under EU NCAP's 5-star safety benchmark. If all milestones align, mass production could begin as early as the fourth quarter of 2026, with customer deliveries in the first quarter of 2027. The pricing strategy is equally bold. Tesla plans to launch the base Model 2 at $25,000, with the butterfly door package costing an additional $1,200, or roughly 4.8% of the total MSRP, a cost footprint nearly unheard of for supercar-style mechanisms. For comparison, the Model X Falcon Wing added nearly $5,000 in hardware and service complexity, while exotics like the McLaren 720S or Ferrari LaFerrari required door mechanisms costing between $9,000 to $12,000 per unit. From a manufacturing standpoint, Tesla faces significant operational thresholds. The global production target for the Model 2 is expected to exceed 1.2 million units annually, meaning more than 250,000 full hinge and actuator sets must be produced each year. Rather than outsourcing to German or Taiwanese component firms, Tesla is reportedly preparing a dedicated hinge and actuator line at Giga Shanghai, projected to cut per-unit logistics costs by 22% and reduce lead time from 18 weeks to just 6 weeks. Still, scaling such a mechanism for a mass-market EV introduces practical friction. Tesla's own service forecast notes that the butterfly hinge system may require recalibration every 80,000 kilometers, adding 8 to 10% higher maintenance costs compared to traditional doors. In cold weather markets, particularly Northern Europe and Canada, where ambient temperatures can dip below -10 degrees Celsius, the system will require EPDM rubber seals with low-temperature elasticity retention, increasing material cost by about $25 per car, but improving long-term durability by 17%. Despite these operational challenges, the move fits squarely into Musk's long-term branding calculus. Each Tesla model historically carries one signature design trait that defines its identity. The Falcon Wing doors made the Model X a luxury icon. The Cybertruck's stainless exoskeleton made it an industrial statement. And now, the Model 2's butterfly door aims to blend practicality with aspirational aesthetics. Internally, Tesla refers to this as premium feel at low cost, PFLC, a design philosophy targeting a 10 to 15% increase in perceived product value with only 3 to 4% added real cost. Market analysts see this as Tesla's way to combat shrinking differentiation in the $20,000 to $30,000 EV bracket. Rivals like BYD Dolphin, $16,000, and Volkswagen ID.2, $27,000, already dominate the affordability and reliability narrative. That's it for the 2026 Tesla Model 2, interior, exterior, and everything in between. Which feature blew your mind the most? Drop your thoughts in the comments, hit like, and don't forget to subscribe with the bell on so you won't miss the next Tesla scoop.